Good morning, everyone. My name is Patricia Pan from American Heritage High School. Last summer, I did a drug design project by engineering a high-affinity BPTI-based inhibitor for human alpha-thrombin using in silico molecular modeling and docking study. So my purpose for my project is basically develop a more effective inhibitor for thrombin so that it can offer hope to help prevent excessive clotting during the CABG, which is the coronary artery bypass grafting and other transplant surgeries, and also become a new drug that can inhibit unnecessary excessive clotting and prevent other cardiovascular diseases. So we all know that we have emergency repair system, which is the clotting system, and thrombin plays a major role. As it is activated, it cleavage fibrinogen into fibrin and help form the clot. Despite the beneficial function of thrombin, errors in coagulation have disastrous effects. For example, it can cause heart attack, stroke, necrosis, but most importantly, it can lead to the failure of surgery, thus increase the death rates of patients. And this shows me that development of a new potent selective inhibitor for thrombin is on high demand. So the specificity or the structure of proteins are usually divided into subsites. As you can see here, the active site of the enzyme are usually divided from S5 to S5 prime, and its complementary pair on the binding loop of the substrate or the ligand is divided from P5 to P5 prime. So what's BPTI? BPTI is called bovine pancreatic trypsin inhibitor, also known as a proteinine. It is a monomeric, which is a single-chain globular polypeptide derived from bovine lung tissue. And there are 4 reasons why I chose this for my study. First of all, it has a relatively small structure, so I can conveniently mutate it with maximum amount of residue, favorite residue on its binding loop. And second of all, it is extremely stable with 3 disulfide bonds and a hydrophobic core, and so it can withstand high denaturation temperature and chemical denaturation. Third of all, there is a very important interaction, which is acid-base interaction between thrombin and BPTI, and I will explain the fourth one later. And due to all of these BPTI features, it was selected as a template for the further mutation. As you can see here, the structure of BPTI is shown on your right side, and 3 disulfide bond color in yellow. At the top is at P1 side, it's a lysine, which has a basic amino acid, and its complementary pair in the active site of the thrombin, as you can see here, color in yellow, it is glutamic acid. So this acid-base interaction suggests me that BPTI can be a really good candidate for my study. So I plan to do a single residue replacement or a subsite mutation first, and my hypothesis toward that is that except at P1 site, which is that important acid-base interaction happen, the rest of the residues mutant should show a higher binding affinity than the existing residues. And after evaluation, the final mutants should be superior than the original one. And also, I did a comparative study with the existing direct thrombin inhibitor, and my hypothesis that they should show a better complementary pair with thrombin. So this is a procedure overview. Basically, I select the model and modify them, and finally run the simulation. So I use 3 different kinds of computer programs. First is called Chimera. I can view and construct the mutants, and the structure is obtained from protein database using high-resolution X-ray crystallography. And then biologically, docking study is very computational commanding, so simplification is required, and Autodock tools enables me to treat the receptor as a rigid structure as well as the ligand, except the binding loop, which means the mutated residue is treated as rotatable and flexible. And the final result is run by Autodock Vina, and its output is usually a score, or we call it binding affinity. So binding affinity is the energy required to let the ligand bind with the enzyme, and the more negative is, which means less energy requires. So the bigger numerical value is, and more favorable or a better inhibitor it is. So I want to introduce you to a MERPS database. It is a protein database. Basically give you information about the protein you are studying as well as its potential inhibitor. This is a screenshot. There are over 330 potential inhibitors for thrombin. As you can notice here, a proteinine is actually one of the 10 that does not have any reference or scientific journal indicated its mutated structure as a thrombin inhibitor. So at the single residue replacement, as you can see from the chart, the pink is colored at original, and the yellow is the mutant score. At P5 prime site, as leucine replaced arginine possess an additional hydrophobic interaction, there is a 1.4-fold increase, as well as at P2 prime and P3 prime is there a 1.2-fold increase. And this suggests me that my hypothesis was proven correct because except at P1 site, the rest show a better binding affinity with thrombin. And then I constructed the final mutants. As you can see here, model 3 and model 10 are the top two scored one, and I compared them with the original templates. And in general, there is a 2.3-fold increase. So with the statistic proven that it is a really good replacement. And then I did a comparative study with Hirudin and argatroban, and I will explain what are those later. And when comparing with Hirudin, there is a 2.2-fold increase, and when compared with argatroban, there's 0.81-fold increase, with a low p-value and a high t-value support my hypothesis that this show a better complementary pair with thrombin, so it has the potential to become a new anti-thrombocoagulant drugs. So in general, they are really significant replacement, and after analyzing the 15 mutants I have shown you before, 11 of them is considered as a good binding, which means their binding affinity is lower than -10. So Hirudin and argatroban was chosen for my comparative study because first of all, they are direct thrombin inhibitor. Second of all, they are really commonly used in the clinical trial. For example, like argatroban is an oral medicine applied for you, and Hirudin is used through injection. So the discovery of this new engineered inhibitor has the potential to develop a new strategy for antithrombotics, which can be widely used daily in life as well as in emergency cases. And most importantly, since thrombin activates procoagulant factor as well as anticoagulant zymogens such as protein C, so the direct inhibition of thrombin can stop coagulation while prevent temporary hemophilia. And since the development of a new inhibitor is proven to be more effective than the existing one, so this might help solve the dilemma in medical field. As you can see here, protein C is activated by thrombin. So in the case of CABG, medicine derived from this inhibitor can help reduce the post-operative surgical coagulation at surgical site, and it may also have the potential to reduce death rates during the invasive surgical procedure as well as post-operative illness. And similar medicine derived from this inhibitor can provide treatment for acute coronary syndrome or embolism, such as deep vein thrombosis, and help prevent thromboprophylaxis in atrial fibrillation, stroke, cardiac infarction, and so on. And since the special property of thrombin, which keep a balance between anticoagulant and procoagulant, so this direct inhibitor may be suitable for long-term treatment and may be the key in emergency cases. So in my future research, I would like to use a more accurate or reliable procedure or technique called molecular dynamic. This gives you the information about how this ligand and enzyme complex is performing over a different time scale, and most importantly, they give you the information about how solvent plays a major role in helping this protein ligand structure to move forwards. And this can suggest the MD, which is molecular dynamic, can suggest a very good superior candidate for the following in vitro mutagenesis. And after mutagenesis, enzymatic study should be applied. Thank you.
I noticed you're using a trypsin inhibitor. What is trypsin?
Oh, trypsin is a protein, with a special amino acid.
Oh, okay. And how do you make a genetic mutant?
Oh, use a computer program. So this computer program allowed you to do a rotamer, which means it's like you change the residue, and this help you score or give you the binding affinity.
And you replaced leucine with arginine. Why did you choose arginine? How does it differ?
Yeah. because I want to show you here. So there is a thrombin specificity matrix, tell you the preference of different enzyme toward different residue, and by using that I can narrow down my choices for rollimers, like which one I would choose, because I've already known that thrombin is more likely to bind with them.
The data collection on the kilocal per mole.
Yeah.
What kind of instrumentation do you use to get the data?
Oh, the computer, I write a command for the computer to run it, and it came out automatically with like a delta G, gives free energy in these units.
So I was just wondering, so you had your Chimera software. Did you input the information to make those structures yourself, or was that?
Well, I did all the information by myself, and I read a lot of scientific journals. Like some of them, especially when you download them from the website, they give you instruction how to find protein from the protein database, and then you can construct them in that software.
So the models that were made were from previous journals?
Yeah, it's the protein database is like store all the protein that has been discovered in the world.
And then you had your top 15 that mutation that you showed.
Mm-hmm.
How many actually did you do overall to get those 50?
I actually did over 100 run models, because first of all I want to make sure that the computer didn't give me any false results, so I run them twice to make sure that all of them are accurate. And since at the single residue I do all the 20 amino acids, and to choose the top score one and combine them to do like a mix and match.
What school you're in?
What school do I go to?
Yeah.
American Heritage.
Okay, let's just you can choose.
Oh.
The school is.
Okay. And so for your molecular modeling, that was sent off, so you sent that somewhere?
No. Actually, because it's not I work with a professor, but okay. I'll finish here first. So I work with a professor, and he told me that it's like nowadays with as age, like people starting to get age, and there are a lot of problems with coagulation. So I was wondering so it's like the problem of thrombin, so that I started doing this, and he suggested me with like 3 different computer programs, because I choose the best of their function. So that's how I chose this, and then this I put them in, like put the molecule or the modeling in by myself.
Thank you.
Yeah.
Thanks.
Okay.
Thanks again.